Hey everyone, in this video we're just going to do a few quick examples of L'Hopital's rule. I already assigned a different video that cover most of the concepts, so I'm just going to do some slightly different examples and just kind of recap a little bit of what was explained in the other video. So first of all, when we find the limit of something like this, what we did at the beginning of the semester, the first thing is, right, with limits, you plug it in and then see what you get. If you get a number, you're done. If you get 0 over 0, that means do some algebra. So here, when you plug this in, you're going to have 2 squared, which is 4, plus 2, which is 6 minus 6. So you're going to have 0 over 0, which means it's an indeterminate form. So back in chapter 2, what we were doing was saying this is the limit as x goes to 2, and this meant do some algebra. So we factored, which factors into x minus 2x plus 3 over x minus 2. And then we said, like, oh, look, you can cancel those. So you're really just left with the limit as x goes to 2 of x plus 3, which is 5. Now, doing it this way, the nice thing about this is that then I can see, based on this limit, that this graph is going to have a hole at 2, 5. If I just do the limit using L'Hopital's rule, I'll just know what the limit is, but it doesn't necessarily tell me that there's a hole there. And so, right, it could be a different kind of discontinuity because of the limit. So here, right, L'Hopital's rule, or L'Hopital's rule, what it says is that if you have the form 0 over 0, or infinity over infinity, so these are indeterminate forms, then the limit as x goes to a of whatever your two functions are, f of x over g of x, is the same as the limit as x goes to a of the derivative of each of the functions. Not a quotient rule, but just the derivative of the numerator divided by the derivative of the function in the denominator. And then this will be the same limit. And so a quick proof of that, we'll do it for the 0 over 0 case. So in order to have the 0 over 0 case, that means that f and g are continuous functions. So let's say f and g are continuous functions and differentiable. We have to have the derivative exist so that we can take the derivative with f of a equals g of a, which equals 0. And let's make a note that the derivative g prime of a is not 0. So in order for us to get 0 over 0 with the limit as x goes to a, that means that when you plug in a, f of a over g of a will give you 0 over 0. So that's what that means, that f of a equals 0 and g of a equals 0. So they equal each other and they are equal 0. So let's look at the limit then as x goes to a, and I'm going to start with the other side of f prime of x over g prime of x. So what is this limit? Now recall from earlier in the semester, so chapter 3, I believe, the definition of the derivative, right, f prime of a means this is the limit as x goes to a of f of x minus f of a over x minus a. And we can change that to g or h, k, any name of the function. So, but what that allows me to do is that then I already have the limit here as x goes to a. So f prime of x, so f prime of a will be f of x minus f of a over x minus a. So I can replace this with this, and the same thing for g prime of a. So this will be g of x minus g of a over x minus a. But notice that here my x minus a's cancel, divide out. So I'm just left with, what are we left with? The limit as x goes to a of just f of x minus f of a over g of x minus g of a. But what did we say about f of a and g of a? They're 0. So f of a is 0, g of a is 0. So what are we left with? Just the limit as x goes to a of f of x over g of x. And so notice that we start with the limit as x goes to a of f prime over g prime. And then we have it, then that is equal to, so this limit is equal to the limit of just those functions. So that is essentially what L'Hopital's rule is telling you, that if you have the limit as x goes to a of f of x over g of x, this is equal to the limit as x goes to a of f prime of x over g prime of x, right? And I can do this for any f prime of a, so for any a where the functions are defined, so that's why I can generalize this f prime of x to be that. And this is for 0 over 0 or infinity over infinity. So those are our indeterminate forms. So let's try a few examples, hopefully different than the ones that you saw on the other video that was assigned to you. So let's start with this 3, and let's see what form are they. Do we have an indeterminate form, or can we just plug in the value and we're done? So when I plug in 1 to ln of 1, well, ln of 1 is 0, so I know I'm going to have 0, and 1 minus 1 is 0. So I have 0 over 0, so L'Hopital's rule applies. And notice that essentially here, because I can't do any algebra, then it's best to use L'Hopital's rule. If you can do algebra, I would say just do the algebra. Sometimes it's easier to just do the algebra than to try to take the derivative of something. As for b, as x goes to 0, let's see, sine of 0 is 0. So you have 0 minus 0 there. So 0 over 0 minus 0. So 0 over 0. And here as x goes to pi over 2 from the left, that is a little bit hard to see, but there is a little minus right above there. So as x goes to pi over 2 from the left. And so oftentimes you'll see these because that means that at pi over 2 is a vertical asymptote, sorry. It's a vertical asymptote. And so that means that you want to be able to see from one of the sides. So you might see a plus or you might see a minus depending on what kind of limit we want to find. So, but oftentimes when you see a plus or a minus in there, it's because you have a vertical asymptote at that point. So technically here, as x goes to 1, well, no, that doesn't give me a vertical asymptote. Oh yeah, it does, but so we could have a plus or a minus there. I didn't put one in there because it's really the ln of x is not, if it was going to 0, I would want to put 0 from the right because of the domain of natural log of x. All right, back to this one. So here, as x goes to pi over 2 from the left, so tangent of pi over 2 from the left over then secant of pi over 2. Now this one's always going to be, because it's square, that's going to give us a positive. So I'm going to have secant of pi over 2. Secant, remember, is 1 over cosine, so that's going to be an infinity. So it's going to go to infinity. What about as x goes to pi over 2 from the left, or tangent of x? And so here you may want to remember your graph for tangent. So what does tangent look like? Tangent is the one with all the vertical asymptotes at the pi over 2's. And so, and it looks like the, kind of like the cubic function. So this is tangent, and it just kind of continues like that, right? This is 0, this is pi, and you have negative pi over here. Not to scale there. So now that we're looking at this, it says x goes to pi over 2 from the left. So if you're approaching from the left of pi over 2, you are smaller than pi over 2, so you're going this way, so the graph is going towards infinity. So you have infinity over infinity. So in all these examples, the fit the indeterminate forms of in order to use L'Hopital's rule. So that means we can use L'Hopital's rule. So let's start with part A. So for part A, I have the limit as x goes to 1 of 2 ln x over x minus 1. So I can then take the derivative. And what I like to do, which I saw that Professor Leonard also does, is that I like to I usually put an L in here to indicate that I have taken L'Hopital's rule. Sometimes we're just saying equals because we're simplifying. And sometimes we're putting equals and we're taking L'Hopital's rule. We're applying L'Hopital's rule. So here, let's take the derivative. And remember, it's not a quotient rule. I'm just taking the derivative of the top divided by the derivative of the bottom. And so now as x goes to 1, I just get 2 times 1 over 1, which is 2. And that is my limit. For part B, we have the limit as x goes to 0 of 2 sine x minus sine of 2x over x minus sine x. So we already saw that it's 0 over 0, so that means we can apply L'Hopital's rule. And so when you take L'Hopital's rule, that means we're taking the derivative of the top. So the derivative of sine x is cosine. So I'll have 2 cosine x minus the derivative of sine of 2x, which is cosine of 2x, and then by chain rule times 2. So let's put the 2 there, all over the derivative of the bottom. So 1 minus cosine x. And check it again. So plug in 0 and see what you get. If you get 0 over 0 or infinity, we have to do L'Hopital's rule again. If we get a number, you're done. So let's see. Plug in 0. Cosine of 0 is 1. So we're going to have, what is that? I said 1 and I wrote 0. So 1, so it's 2 times 1 minus cosine of 0. So 2 times 1 again, over 1 minus 1. So I still get 0 over 0. So that means we gotta do L'Hopital's rule again. So I'm going to have the limit as x goes to 0 of now the derivative of 2 cosine is negative 2 sine x. And the derivative of 2 cosine of 2x is going to be plus, what's that, 2. So cosine of 2x, the derivative of cosine is negative sine. So that's why it became a plus. Sine of 2x by chain rule times the derivative of 2x, which is 2. So this is going to become a 4 over the derivative of 1 is 0 and the derivative of cosine is negative sine. So minus a minus, so just positive sine of x. But notice that once I plug in 0, I'm going to get 0 over 0 again. So this isn't looking too good. So what do? So we can take L'Hopital's rule again, but now it feels like I'm going in a circle. So what else can I do? Let's look at sine 2x. So instead of taking the derivative, what else can I do? We can rewrite it. Right? I know from my trig identities, sine 2x is 2 sine x cosine x. So let's rewrite it. So notice that now I'm not putting the L because I am not using L'Hopital's rule. I'm just rewriting. So I'm going to have minus 2 sine x plus 4 times sine of 2x, which is 2 sine x cosine x over sine x. And this allows me to then factor that sine x out. So I have factor out the sine x. And again, notice I have not put the L on top because I am not doing L'Hopital's rule. I am just simplifying, doing some algebra. So I'm going to have minus 2 plus 8. 4 times 2 is 8 cosine x over sine x, which then gives me, those cancel. And now when I plug in 0, cosine of 0 is 1, so I have minus 2 plus 8 times 1, which is 8, and so that is 6. So my limit is 6, which just I want to point out that at the beginning here, I could have just, well, I guess with this x here, I did have to take the derivative. I was going to say we could have rewritten sine 2x from the beginning and perhaps cancel, but we can't because of that x. So just kind of pay attention to things like that. Like when you get 0 over 0, right, remember, is either you can do algebra or you can use L'Hopital's rule. Given the chance to do algebra, right, like that's what I'm doing here. I decided to do algebra instead of using L'Hopital's rule again. You can still choose L'Hopital's rule again, and now what's going to happen, you're going to get cosine x on the bottom, and now you're going to have a 1 on the bottom, and your limit will be able to come out. So either way, right, so at this point, I chose to do algebra, but you can do another L'Hopital's. And what's the third one? The limit as x goes to pi over 2 of 2 tangent x over secant square x. So plug in pi over 2. Oh, we already saw that this is infinity over infinity. So this qualifies for L'Hopital's rule. Or can we do any algebra? Let's do L'Hopital's rule and see. So I'm going to say the limit as x goes to pi over 2 from the left of the derivative of tangent is secant square. And then, here the derivative of secant square. Right? Secant square is really secant x quantity square. So when I take the derivative of that, don't forget about the chain rule. So the derivative of that, then bring the 2 down, so it's 2 secant x times the derivative of secant x, which is secant x tangent x. And so that means we can cancel out our secant square. So you're just left with the limit as x goes to pi over 2 from the left of, I guess we can also cancel out our 2's. 2 divided by 2 is 1. So we'll be left with 1 over tangent x, which is cotangent. Or you can write it as sine over, in terms of sines and cosines. So this will be cotangent is cosine over sine. So as x goes to pi over 2, cosine is 0 and sine is 1. So you're left with 0 over 1, which is 0. Now there are other indeterminate forms of limits, and so those are when you have, other forms. When you have 0 times infinity, or infinity to the 0, or 0 to the infinity, or 0 to the 0. So these are all versions of indeterminate forms. And so we want to be able to, when we encounter anything like this, our goal is to turn them into either 0 over 0 or infinity over infinity. So you'll have to do some algebra in order to turn them into those forms. So here, for this example, find the limit as x goes to 0 from the right of x, ln x. And again, from the right here is because of the domain of the natural log of x. Remember, the graph of ln of x is the logarithmic function, this one, y equals ln x. So the domain starts at 0. Domain is 0 to infinity, so we can only approach 0 from the right of 0. So that's why you see that here. So this is then 0 times ln of 0, but notice that as x goes to 0 from the right, the natural log is going towards negative infinity. So we don't necessarily keep track of the signs for L'Hopital's rule, it's just the form, right? It's 0 over 0 or infinity over infinity. So this is the form 0 times an infinity. So when you see infinity, it's really one of the infinities, either positive infinity or negative infinity. So my goal is to write it either as 0 over 0 or as infinity over infinity so that we can use L'Hopital's rule. So sometimes it's which one is easier to rewrite. And what I'm going to do is I'm going to rewrite the x. So I'm going to leave ln x where it is, and I'm going to say this is the ln of x divided by 1 over x. Are these the same quantities? Is x times ln x the same thing as ln x over 1 over x? Yes, right, because when I divide by a fraction, it's the same thing as multiplying by the reciprocal of that fraction. And so this gives me x ln x. So that's the same thing. But now this, when I plug in 0, I have infinity over infinity. Because as x gets really, really, really close to 0, 1 over 0 is getting really big, right? So then this is infinity over infinity. And so this means we can use L'Hopital's rule. So I'm going to say this equals, and I'm going to put my L because I am applying L'Hopital's. So the limit as x goes to 0 from the right of the derivative of the numerator, which is 1 over x, divided by the derivative of the denominator. 1 over x can be rewritten as x to the minus 1. So this is negative x to the minus 2, so negative 1 over x squared. And let's apply our same rule here that when you divide by a fraction, it's the same thing as multiplying by the reciprocal of that fraction. So I have 1 over x then times negative x squared over 1, the reciprocal of 1 over x squared. So I'm just left with the limit as x goes to 0 from the right of negative x, which goes to 0. So that is my limit. So okay, so here, sorry, when you see 0 times infinity, it's really going to depend on the function, because you might be thinking, why did you choose to rewrite the x? Because I think taking the derivative of 1 over x is better than taking the derivative of 1 over ln of x. But the other way I could have written this is to say x and then 1 over ln x. But then I don't really want to take the derivative of that when I do L'Hopital's rule. So I'm going to rewrite the one that is best to take or easier to take the derivative of. So that's why I chose to rewrite the x as 1 over x. So instead of multiplying by x, I'm dividing by 1 over x, which turns out to be the same thing. So let's try the next example. The other indeterminate form is when you have infinity minus infinity. So this is another indeterminate form. Why is it indeterminate? Because they're different functions. So the level of infinity, remember, infinity is not a number, it's just a concept that things go on forever. So, but they are not going to infinity at the same rate. 1 over ln x does not grow at the same rate as 1 over x minus 1 does. And so since they're going at different rates, they are both going towards infinity, but at different rates, they may not necessarily be approaching 0. If they're close to rising to infinity at the same rate, then chances are their limit is going to be close to 0. But in this particular case, we already know ln x is the slowest growing function, so 1 over ln x is not going to grow at the same rate as 1 over x minus 1. So we should expect this to be not 0, hopefully. So we'll see what happens. So limit as x goes to 1 plus, right, plug it in, 1 over ln of 1 is 0, so you have 1 over 0, which is infinity, and 1 over 0, which is infinity as well, meaning they're going to infinity. Infinity is not a number. And so my goal, what is our goal? Our goal is to write it as 0 over 0 or infinity over infinity. So the only way to do that is I need to have a common fraction. So get a common denominator. So I'm going to have the limit as x goes to 1 from the right. And that's, I think, because of this one. Yes, we have a asymptote 1 over x minus 1. You have an asymptote at 1, so that's why we're looking at the limit as x goes to 1 from the right. So get a common denominator. our common denominator is going to be what? X minus 1 times ln of x. So multiply this one top and bottom by x minus 1. So you're going to have x minus 1 over x minus 1 ln x minus, and then this one is the ln x. So multiply top and bottom by ln x minus ln x over x minus 1 ln of x. And now that they have the same denominator, you can combine them. So notice that I do not have my little L on the top, and that's because I am not applying L'Hopital's rule yet. All right, now what happens when I plug in 1? So plug in 1, so you'll have 1 minus 1, which is 0, minus the ln of 1, which is 0. So we'll have 0 on the numerator, and then 1 minus 1 is 0, times 0 is 0. Now 0 times 0, that's not an indeterminate form, that's 0. So now that means we can use L'Hopital's rule. So now I'm going to put my little L there because I am applying L'Hopital's. So this is the limit as x goes to 1 from the right of, take the derivative. So I'm going to have 1 minus 1 over x over, and now here I have x minus 1 times ln x. So we better use the product rule. So product rule says the derivative of the first, which is 1 times the second left alone, plus the first, x minus 1, times the derivative of the second. And let's see what happens when I plug in 1, or can we simplify? If I plug in 1, I'm just going to get 0 over 0 again. So let's try to simplify because I have a complex fraction here. So let's multiply. I have a 1 over x there and a 1 over x here. So let's multiply top and bottom by x so that then I can cancel those 1 over x's. So we're going to have, I'm just simplifying so I don't have the little L here. So I'm just going to have x minus 1 over x ln x by multiplying the whole thing by x, and now this 1 over x is going to cancel. So plus x minus 1. And so when I plug in 1, I get 0 over 0. But at least it looks a little better for me to be able to apply L'Hopital's rule again. So this is the limit as x goes to 1 from the right of, take the derivative. So that's going to be 1 over, and here I have x times ln x. So I need another product rule. So the derivative of the first, which is just 1 times the second left alone, plus the first, so x times the derivative of the second, and then plus now the derivative of x, that's 1, and the derivative of 1 is 0. Now what happens when you plug in 1? So notice that the numerator is already 1, so I'm going to have something, either infinity, negative infinity, or I'm going to get a number. So ln of 1 is 0, and this is 1 plus 1 is 2. So our limit is 1/2. So infinity minus infinity is not 0, right? Especially this means our functions are not growing at the same rate. Sometimes they'll be 0 if the functions grow similarly, but infinity minus infinity is not necessarily 0. In this case, infinity minus infinity is 1/2. Now my last example. This example, can you already tell what the limit is? So this, in the video that was assigned to you, what you saw was that the limit as x goes to infinity of 1 plus 1 over x to the x was something. What was it? It was e. And so here, what is this limit? Notice that it looks very similar. So my question to you is, can you go back to that video or look at your notes? Can you recreate the steps for this problem, they're gonna look very similar. Like they're gonna have the same, everything's gonna look the same. Instead of 1 over x, you're gonna have 3 to the x. So when you have the limit as x goes to infinity of, what is it, the e to the natural log of 1 plus is going to look like 3 over x to the x, and then continue this. So my question to you is, can you see what this limit then is going to be? You're going to end up with e cubed. So that is the limit. And then, so what about the limit as x goes to infinity of, say, 1 plus 1 minus 2 over x to the x? Can you guess what that limit is going to be without doing too much work? Yeah, it's going to be e to the minus 2, because you're essentially redoing that same work, but what changes is just that little number in there. And so everything's going to be, all your work is going to be exactly the same except for that constant. So this is a nice little limit to know when you get to Calc 2 and you're doing series. It's going to come in handy to know this limit, mainly this limit. As x goes to infinity, 1 plus 1 over x to the x is e. The other version of this is that the limit as x goes to 0 of 1 plus x to the 1 over x, that's e as well. So essentially notice that it is 1 plus a little bit to the infinity. So when you have that setting, so when you have 1 plus a little bit, I know, very technical here, because this isn't actually 0, right? That's not actually 0. You're getting close to 0. So it's 1 plus a little tiny bit to the 1 over 0 is to the infinity. Then this has something to do with e. And so notice here, right, 1 plus 3 over x. So that's still 1 plus a little bit. As x goes to infinity, 3 over x is getting close to 0. It's not equal to 0, so it's just getting close to 0. So it's 1 plus a little bit to the infinite power. So that has something to do with e. What to do with e? E cubed. This is 1 minus a little bit now. So, but you can say 1 plus a little bit, and the little bit just happens to be a negative number. So 1 plus a little bit to the infinite power has something to do with e. What something to do with e? E to the minus 2. So 1 over e squared. And so on. So if you have essentially 1 plus a little bit to the infinite power, has something to do with e. So I encourage you to try some of these examples and notice that you always get e to some power. All right, email me if you have any questions.